Hey, welcome back. This is Mr. Kelly at Kaiserslautern. Now, this lesson is a doozy, so we're going to jump right into it. We're going to talk about compound probability and independence. They're two different things. Compound probability really means that we have a couple of things going on at the same time, and independence, we'll talk about that in a few minutes. But here are some rules for events that are independent. You know, the short story is independent means that one event, whether it happens or not, will not affect the other event. So if we have events A and B, independent would mean that, you know, if A happens, if A doesn't happen, doesn't matter. B is going to happen at the same chance or the same likelihood or probability. Okay, now what I want to do is I want to give you the two rules here. We have two rules, two rules for events. One is the intersection. Remember, intersection is the same as and. So if we have A and B happening, then the rule is we just multiply their probabilities. Okay, that's pretty easy to remember. And if we are going with a union, which is or, so the probability of A or B, then what we do is we add and we have to subtract the part that is both. Now, what I'm going to do is I'm going to call timeout and I'm going to go back to the last lesson.
Okay, so this takes us back to the last lesson. If you remember, there was an example about boys and girls and which one preferred Bruce, Kelly, or Sullivan in their videos. I eventually had you do some problems all on your own. Now,
So here's what I want to do. I know this is the last packet, but just stay with me here for a second. Just watch. I want to show you where this formula comes from. I'm talking about the probability of A or B. All right, and the formula that I gave you was the probability of A or B equals the probability of A plus the probability of B, and then we have this part where we have to subtract minus the probability of A and B. I'm going to show you what that means according to this table. Now, we did this table last time, and what I want to focus on is this. Whoa, that was psychedelic. I want to focus on this one right here. The probability of brust or that the student was a boy, if you remember this. So the way we did this, all right, the formula works. The probability of A or B. We want the probability of A. So in this case, we'll say that that's brust. All right, so we want that whole column. And then we want the probability of B, so we add that. Now, if you notice, one number got selected twice. It was that one right there. Now, what is that cell right there? That cell is the probability you're breast and a boy. That's this part right here because we counted it twice. So if you want to use a formula instead of the table for or, the probability of A or B, the union here, you can just add them, but you have to subtract the part that is both. That's where that formula comes from. So I'll bring you back to our packet now. Hope you enjoyed that trip. That's what we're looking at right here. And as a little, favor to you, what I normally do is I will usually ask you to find the intersection first because I know you need to use that when you find the union. So most of my questions will go like that, but maybe once in a while they won't. Just keep your eyes open. So here are the two formulas that you need to know. The intersection, A and B, we multiply, and if it's or, the union here, that we're going to add them, but you have to subtract the probability that they're both. And remember, these are for independent events. I don't think I specified that before. So, the events have to be independent of each other, which means, one does not affect the other. We'll talk about that some more later. First example, algebras make a lot of algebra typos, especially this guy here. Had to give that guy. Let event A be the algebras make a typo in a packet, and the probability of event A is zero point 0.5. And let event M be the algebras make a typo in a mastery check, and the probability of that is zero point 0.2. So suppose we pick a random packet in mastery check. What is the probability that the algebras make a mistake on both the packet and the mastery check? So this is essentially what we want to find here is the probability of the packet and the mastery check. And according to our formula that's up here, that would be the probability of A times the probability of M, right? So they gave us the probability of A is zero point 0.5 and the probability of M is 0.2. So you work all that out, what are you going to get? Be, 20% of 5. What's 20% of 5? Zero point 0.1. Boom. So that's the probability of A and B. Now, what is the probability that the algebras make a mistake on a packet or on a mastery check? So that uses the other formula here. The probability of A or M is going to equal the probability of A plus the probability of M and then you have to subtract the probability of A and M. And as I said, I'm usually pretty good. I give you that one right there. Look, we just figured that one out. So the probability of A and M is right here. So that's what that value is going to be. So this is all going to equal 0.5 plus 0.2, and then we have to subtract 0.1. And that grand total, what do you get? 5 and 2 is 7, minus 1, that would be 0.6. Okay, so that's the probability of A or M making a mistake on either a packet or a mastery check. Okay, so what if they give you a question like this where you're given a 5-question multiple choice quiz and there are 4 answers for each of you to choose from? You decide to randomly guess on the first 2 questions, so take it like you're Sully. What is the probability that you get the first 2 questions correct? So really, we have an event here. You want to get the first one correct and you want to get the second one correct. So what is the probability you get the first one correct? On this situation here, there are 4 answers and you're going to choose one of them. One of them is correct. So the probability you get the first one correct is 1 out of 4. The probability you get the second one correct is 1 out of 4. And so we just need to figure out what that value is. That'll work out to 1 out of 16. Okay, so that was easy enough. What is the probability you get at least one of the first 2 questions right? So that means you get the first one right, or you get the second one right, or you get them both right. Okay, so that is going to use our formula right here for the union of 2 events. So that would equal the probability of getting the first one right, plus, there's where we're looking right here, plus the probability of getting the second question right, and then we have to subtract the probability of getting them both right. Now, we already figured that out, but I'm going to write it out. Okay, remember that's this value right here. That's the probability of both right there. So 1/4 and 1/4 is 1/2, and then we have to subtract a 16th. Oh my goodness, what does that all equal? Like 7/16? Ugh. Now, hey, can we use a calculator on this? Absolutely. You can get yourself a decimal. 0.4375. Okay. Now, next question. What's the probability you guess on all 5 out of 5 and you get them correct? So really, you have to get the first one right, and then the next one, and the next one 5 times. So I'm just going to use an exponent for that. We're going to use a calculator. It's 1/4 to the 5th power. So calculator here, 1 divided by 4, and we want to raise that. Remember, that's this button right here to the 5th power. And as I said, decimals are okay. Oh, we got to know, we got to understand that. Please don't say that's 9 points. Bring that back up here. Somebody bring that back up here. Bring that back. Let's drag that down so we can look at it. Come on now. Look at that number. It's 9.76. That doesn't make sense of probability, but look right here. Please don't ignore that. Little tiny e. That is scientific notation. That's what we're talking about. Use some scientific notation all across this nation. What does that mean? We got to move that 4 times. 1, 2, 3, 4. So we got a 0.0097. So the probability of that is 0.000. We have 1, 2, 3, 4. We have 3 zeros and then the 9. All right, 765. I'll just keep going far enough that I don't have to round it. How about that? I don't have a specification for how far you got to round. But that's pretty small chances. If you guess on 5 questions, you get them all right. Not going to work. So as we do more and more of these problems, I understand they're pretty complicated. So one of the tools we can use to help us is called the Venn diagram. And I think you've seen them before. They're to the rescue. Now, you can use them with totals or with probabilities. So we'll use the totals first. So suppose we have a class of 45 students and 20 play a sport and 15 are in JRTC and 10 participate in both JRTC and a sport. I want to draw a Venn diagram here. So let us define these variables or these events here. We have S will be the student is in a sport, and then J will be the student is in JRTC. So let's draw a Venn diagram. So do you know what a Venn diagram is? It's a circle looking thing. Looks like a circle because it's a circle. And then we have another circle. And then we always put a box around the outside because there's always a possibility that something is not in either circle. So we have a class of 45 total students. So let's just, keep that in mind. 45 total students. 20 play a sport. But it says, but you have to go to this. 10 are in both JRTC and a sport. So I'm going to start there. There are 10 students here, which means, let's define this. Let's this be S. That'll be the sport. This will be J for JRTC. So if this circle is S, and there's a total of 20, so that's what's in S. But 10 are here in the middle, right? Because it's in both S and it's in sport and JRTC. That means that there must be 10 right here. Now we have a total of 20 in sports. Now JRTC that has 15, so that's total. That includes that 10 that's in both. That means there's 5 out here. Then we go to the last part. There's 45 students total. Right here we have 25. That must mean 20 students are out here. Okay, so this is a Venn diagram. It's not too difficult. You draw two circles, and one represents one event, one represents the other event, and then the part that's overlapping here in the middle is always both happening at the same time. So let's find each of the probabilities. The probability that you're in a sport. So we need all of the S. So all of the S is how much? 20. It's not 10, it's 20. Remember they told us that way up here. So it's 20 out of how many students? 45. What's the probability you're in JRTC? Well, look at the whole circle. That's 15 out of 45. What's the probability that you are in a sport and you're in JRTC? That's this part right here. That's that part. You're in both at the same time. Okay, so that would be 10 total students out of 45. The probability that you're in a sport or JRTC. That's this one or this one or that one. Now remember, in math, when we're doing probability, if you're in both, that counts as or. It means at least one, I mean one or the other or both. So total number of students, 25 out of 45. Now here's a tricky one. This says the probability that you're in a sport, given that you're in JRTC, that conditional probability right there, given that you're in JRTC, that means I'm only looking at the JRTC kids. That's all I care about. I don't care about any other part of this picture. So this is the only part of the picture I care about, right here. So what is the probability that you're in a sport? Well, before we figure that out, it's out of JRTC. So JRTC is only 15. So this one's going to be out of 15. And the probability you're in a sport, how many of those kids? 10. See how that one's a little different? So when we have conditional probability, you're only looking at a subset here. This only part of the Venn diagram, just the J part, given the J have a JRTC. So that's what you're looking for right there. All right, F. Ooh, let's get that shading out of the way. The probability that you are not in J and you're not in S. All right, so let's use a highlighter again. Not in J. So that would be everything. If I were going to highlight not in J, that would be this. That would be all the way out here. This area right here is not J. Right? That's that part. And though you have to be not S. So for not S, I'm going to use this lavender color. Oh, that's nice. So here's S. So everything on the outside, this is... Ugh. So this lavender is all on the outside of S. All right. Now I don't know how clear this is, but to be not J and not S, we're talking about this area just on the outside. That's the part that was double shaded. It was both of those. So how many kids are in that area there? Well, 20. That's 20 out of 45. You can see that there. Okay, so that's how we can use a Venn diagram. Let's try it when they give us probabilities. When Sully was a senior in high school, he applied to two colleges, the Ohio State University and Miami University, not in Florida. He was pretty sure that the probability to get into OSU was 0.4 and the probability to get into Miami was 0.5. He also thought the probability to get into both is 0.3. So let's make a Venn diagram. Let's make event A that he gets into Miami and event O that he gets into Ohio State. So I'm going to draw my two circles here. All right, draw my box on the outside. Perfect. Probability gets into OSU was 0.4. Always start at both, the intersection here. That's both A and B. Let's make this, we'll make that Miami, we'll make that Ohio State. So Miami, let's see, probably get into both is 0.3. So right here we got to put a 0.3. Right? That's coming from here. Now the probability getting into OSU is 0.4. So this whole thing has to be 0.4. That means that this part is 0.1. And for Miami, it's 0.5. So that means that this part here must be 0.2. So now when I add all these together, I get 1 plus 3 is 4, and 2. This gives me 6/10. That must mean that 4/10 is out here. Easy enough. That's our Venn diagram. So, the best part about a video is you can stop it and rewatch it if it's a little too much for you. So you can go back and do that. Part B, what is the probability that neither university accepts Sully? So what part of this? If he gets in any part of either circle, then he's in a university. This one right here is only Miami. This is all of Miami, including both. Okay, the point 3 is he gets into both colleges. And the point 1 means he's only accepted at Ohio State and not Miami. This probability right here that he is accepted at Ohio and not Miami. Okay, and then the point 4 is neither, nothing. So what is the probability that neither university accepts Sully? So the probability, let me write this out, that he does not get into Miami and he does not get into Ohio State is 0.4. Boom. And we're done with that one. So notice the difference. This one has counts. This one has probabilities. They both work the same way. Now we got to talk about independence. Okay, two events are independent. This is super important. Two events are independent if the outcome of one event has no effect on the outcome of the second event. Okay, independent events are not affected by previous events. So we do have a formula to check this, and this shows up a lot. You're going to notice that it's kind of important. What this says is if two events are independent, then the probability of A, given that B happened, is still the probability of A. That's what this formula means. The probability of A, given that I know B happened, is still the probability of A. Now, can you do it the other way around? Absolutely. You can do the probability of B has to equal the probability of B given A. Notice how I switch letters and I switch directions. It's okay. The probability of one thing has to equal the probability of that happening given the other event. This is how you check for independence. So let's see how it works here. A quick survey found that 56% of K-Town students live on base, 62% eat lunch at school, and 42% do both. Okay, find a probability of a randomly selected okay, I'm going to do a Venn diagram for this. It says find the probability that a randomly selected student doesn't live on base, nor does he eat at school. That means not one and not the other one. Whoa, Venn diagram. So let's make B for base, because it's all about that. Eat lunch. Let's make that an L. So we found, remember, always go to the part where they do both first. So that's 0.42. Now, quick survey. 56% live on base. So 42% do both. So that leaves 14% for this side, right? Because these two have to add up to that 56. On the other side of it, 62% eat lunch at school. So this must be 0.20. Now when I add all these together, what do I get? 56 and 20 is 76. So this must be 24 out here. So part A, find the probability that a randomly selected student, so I'm going to pull a random student from this Venn diagram, doesn't live on base, so that's outside of the circle B, nor does he eat at the school. So really what I'm looking at is I'm looking at everybody that is neither. That is all around the outside, not including the inside. And we found that probability to be 0.24, so 0.24 for that. Can we write the probability statement? The probability that not on base and does not eat lunch equals 0.24. And here's the question. Is living on base independent of eating lunch at school? So whenever you see the word or they're asking about independence, let's use this formula right here. So we just need to find the probability that living on base is equal to the probability that you live on base given that you eat lunch at school. So how can we figure that out? Let's do it. What's the probability to live on base? So the probability to live on base are these two things. All right, let's make some room here. So Kelly, make some room. Just do this in your notes. Boom. Probability to live on base is, we said that before, 0.56. Now, here's the thing. Can I tell you the thing? The probability to live on base, given that that you're eating lunch. So I really now only care about this circle right here. So this part of the Venn diagram right here is all of the students. That represents all of the students that eat lunch at school. This probability statement is the probability that you live on base given that you eat lunch. So this is out of all of the students who eat lunch. That is what? 0.62, right? They tell us that right here. Now, out of that 0.62, how many live on base? These kids. All right, 0.42. All right, I'm going to talk you through that again. We have the probability that you live on base has to equal the probability you live on base given that you eat lunch in school. That's how we do independence. We have to use our independence rule up here. So the probability to live on base, just add those two together. That's in the B. The probability that you live on base given that, if I say that loud enough, given that you eat lunch in school, it's only out of the lunch. That lunch is right there. That's all the kids that eat lunch. So it's out of 0.62. So we need to figure that out in the calculator to see if it equals 0.56. All right, so here we go. Moment of suspense. It equals 0.67, 68 if we round it. So this is 0.56. This is 0.68. They are not equal to each other. So the answer to this question is no, they are not equal. So the probability of B does not equal the probability of B given L. Okay, so whenever they ask you for independence, you try that. All right, so last example, you try it on your own.
Here's my advice when you try that one. Let's draw a Venn diagram. Work a Venn diagram out, try that one, and then come back and we'll work through it together. Okay, last example here, number 6. The following table of research shows probabilities compiled by dentists of students at Ramstein. Sorry, Ramstein, but we're talking about cavities and halitosis. Do you have them? So here's a little table here. Notice that this section of the table means you have both. This part of the table right here means that you have halitosis, but you don't have cavities. By the way, you don't know what halitosis is? Give it a Google search. All right, so the first thing we need to do, I'm going to draw a Venn diagram. Here we go, Venn diagram. So let's fill out this Venn diagram so we have something visual to look at. We have halitosis, we have cavities. So the part that's both here is 0.09. I'm going to put that right in the middle. Boom. And then what do we got? This 0.18, that means yes to halitosis but no to cavities. So that's going to go right here, 0.18. And then 0.24, that is yes to cavities but no to halitosis. And then neither is 0.49. So now we have our Venn diagram we can look at. The first question is, what is the probability that a randomly selected student has cavities? So I'm going to show that as P of C. And that would be this entire, let's do a little highlight, shall we? This entire circle, that is cavities. So we need to add those two pieces together. And when we do that, what do we get here? 0.33. And then, well, that part's done. Part B is the probability they have cavities and halitosis. So that would be the part that's just in the middle here. So that's just going to equal 0.09 because that's, what represents both. Has halitosis if it's known they have cavities. So if it is known they have cavities. So just reading that makes me say, well, we have some conditional probability here. Given that they have cavities, what is the probability of H? All right, so to do that, I'm going to look, given that they have cavities, I'm only looking at this part right here again. And I want to know what is the probability they have halitosis, which is this little part in the middle. So really this is 0.09 out of the entire piece right here, which is 0.33. And if you work that out, you get somewhere around 0.27. All right, you have to put that in the calculator. And lastly, is having cavities independent of having halitosis? So to figure that out, I'm going to look at the probability of having cavities using our rule and see if that equals the probability of having cavities given that they have halitosis. So let's see what we have. Some of these we already have done before. Probability of having cavities is 0.33. We have figured that out. And the probability of having cavities given that they have halitosis, this is a little different than what we've done down here. So we want, given that they've had halitosis, that's this part right here. So it's out of those two, which is actually out of, we got their 0.27. And then the probability they have cavities, that's this part of the graph. So it's 0.09. So this is the same as 9/27, which is the same as 1/3, which guess what? That's the same as 0.33. All right, so they're pretty close. So if they're close, then we say, yeah, yes, they are independent. It doesn't matter whether they have halitosis or not. The probabilities are the same, so they are independent of each other. That's it, peeps. All right, that's a compound probability and some independence for you. You know, this is intense. This is like camping. If you have any questions, ask your teacher. Mr. Kelly in K-Town. Remember, it's nice to be important. More important to be nice. See ya.